Hi everyone, my name is Liron Aravot. I'm Senior Software Engineer in the Cloud Storage Group in Red Hat. Today I'm going to talk about a project called oVirt. oVirt stands for Open Virtualization. Basically what oVirt does is let you easy way to set up, run, and manage your own data center or private cloud. How do we do that? We do that by managing everything related to virtual machines, high availability, storage, network, SLA, and whatever you can think of. Today, I'm going to talk about ways in which we manage shared storage. As you see, the topic of this presentation is SPDM. So SPDM is our new approach to manage shared storage. I'm going to talk about our old approach to manage shared storage. Then, about our new approach to manage shared storage. I'm going to compare the differences between those two approaches, and later on we'll have a quick debugging session to see how it looks in the real life. So, okay. So our agenda for today. We start off with talking about the old approach that we used in order to manage shared storage. It's called SPM, which stands for Storage Pool Manager. We'll move on later on to talk about SPDM, our new approach to manage shared storage. Later on, we'll have a quick demo debugging session in which we'll inspect actual logs to see how those two different approaches look in real life. And we'll talk later on about our future plans, and eventually we'll have some time for questions. So let's start off with talking about the SPM architecture, which is, I remind you, our old approach to manage shared storage. So SPM, as you can see, stands for Storage Pool Manager. In the SPM approach, one host is assigned with the master role, or the Storage Pool Manager role, and this host is the only host which is allowed to perform create, update, and delete operations of the oVirt storage entities like disks on the shared storage. So let's take an example flow. Let's assume that the user wants to move a disk. So he sends a request to the oVirt engine through one of our amazing APIs, stating that he wants to move the disk from the source storage domain to the target storage domain. The oVirt engine forwards the request to the Storage Pool Manager. The Storage Pool Manager creates the target image volumes or the disk on the target storage. Then the SPM copies the data between the source and the target. And eventually, after the copy finished, the SPM cleans up and deletes the source image. So we can see that in this approach, the only host which is allowed to perform operations on the shared storage, and I'm talking about create, update, and delete operations, as all the hosts in the data center may run virtual machines that access the shared storage and write to it. So the responsibility for performing operations on the shared storage resides on the SPM, or the Storage Pool Manager. So, in the SPM architecture, the SPM performs all the shared storage operations. One problem with the SPM approach is that the SPM is single point of failure. As the SPM is the only one allowed to perform operations on the shared storage, if we lose connectivity to the SPM, or if it crashes, we basically reach a state of failure and we can't perform any more operations before we assign that role to other hosts in the data center. The SPM architecture is very easy to manage. We assign that role to one of the hosts in the data center. Then every request involving operation on the shared storage is forwarded to that host, and everything is nice and easy. Under scale, the SPM architecture is somewhat problematic. For example, we just saw the move disk scenario, but what if I want to move 50,000 disks or 200 disks simultaneously? As only one host performs the operations, under stress, we will probably hit some problems or perform less good. Okay, so The SPM approach is good, it works, and many people are happy with it, but we wanted to improve stuff. So basically we came up with the SPDM architecture. So what do we have in the SPDM? If we saw in the SPM architecture that one host is responsible to perform all the shared storage operations, basically in the SPDM approach, we remove responsibilities from the SPM and assign those responsibilities to the other hosts in the data center. Because if we have 50 hosts in the data center, there's no reason that the SPM will be the only one performing the shared storage operations. So how do we do that? First of all, in order to protect our data and avoid data corruption, we still need to keep we separated the operations that we do into two types. The first type of operations is metadata operations, which are create, update, and delete operations on the shared storage of the oVirt storage entities, like disks, volumes, and so on. So basically what's typical about the metadata operations is that they are very quick. Those operations are very short. For example, I want to create something on the shared storage. Let's take 50 terabyte disks. I want to create it. So the operation of creating the disk is very quick, allocating storage. The thing that takes a long time, the move disk example that we saw before, is to copy the data, the 50 terabytes, from the source to the target. So the operation of creating a disk is very fast. So that operation is a metadata operation. So all the metadata operations are very short operations. As I said, they are create, update, and delete of oVirt storage objects or entities. In this case, a disk, a volume, or a storage domain, for example. All those metadata operations are still performed by the SPM. In order to avoid data corruption, we need to synchronize between the writes and, or more correctly, not writes, but shared storage allocations. So we still keep the SPM role or the SPM for performing these operations on this phase of the implementation. When we'll reach the future plan slide, we'll talk and see what we plan to do with the SPM. The second type of operations that we have are the very long operations. If we talked about the move disk example before, so as I said, copying 50 terabytes of data is a very long operation. So this is the second type of operations that we have. They're usually very long operations that involve a lot of I/O. In the SPDM approach, those operations can be performed by any host in the data center. So let's take an example flow, the move disk flow that we saw before. So as we saw before, the oVirt engine got the request from the user to move the disk and forwarded it to the SPM, which created the disk on the target domain, then copied the data, and eventually deleted the source disk. So in the SPDM approach, this flow looks a bit different. So the user sends a request to move the disk to the oVirt engine, the same as before. The engine sends a request to the SPM to create volume on the target storage domain. Then, if the disk has two volumes, it sends another request to the SPM to create another volume on the storage domain. So the first thing that we can see is that the engine is the orchestrator of the flow now, opposed to before, in which the engine just forwarded a request to the SPM saying, move the disk from here to there. Now the granularity of the operations is much greater. And if we have a failure during the flow, the engine can know the state of exactly where we failed. So we can see that the engine sends one request to the SPM to create a volume on the target domain. Then it sends a request to create a second volume on the target domain. And then in order to perform the long operation that involves a lot of I/O, which is the copy operation, It distributes the copy of each volumes between two of the data center hosts. You can see it on the bottom line in the drawing, that host A copies one of the volumes data to the target domain, and host B copies the other volume data to the target domain. So we can see that each host can perform the copy after the storage entity is created, and the SPM deletes the source image as before. So, sum up. Another neat feature of the SPDM approach is entity polling. As we wrote a new approach to manage shared storage, or more correctly designed new architecture, we wanted to solve another problem. What happens if I send a request to one of the hosts? I just go one step backwards and say that when we use the SPM, all the operations were performed by one host. Now we distribute the operations between large number of hosts, and when we do so, the risk of having one of the hosts performing operation failing increased as well. So basically, as part of designing the architecture for that approach, we wanted also to be able to determine what's the status of the operation in case one of the hosts performing it fails, crashes, or we lose the network connectivity to it. So basically what we implemented, we call it entity polling. We use entity polling when one of the performing hosts is non-responsive. So let's assume that, as we saw in the drawing before, we sent a request to one of the hosts to copy data from the source volume to the target volume, and then that host became non-responsive. So we use it in order to detect what's going on with the operation. So that host performs the copy, but what do we report the user? Although the engine lost connectivity to the host performing the operation, the host still has access to the storage, and it may be performing the operation. So how do we do that? Basically, in order to perform entity polling, we assigned generation to each of the oVirt storage entity. So for example, when you create a disk or you create a volume, that entity is assigned with generation. When we send a request to us to perform operation, once the host completes the operation, it increments the entity generation. That way, even if we lose connectivity to that host, we can use another host which has access to the shared storage to poll the entity. If the other host reports that the entity generation was incremented, we know that the operation ended successfully. Okay, so we sent a request to us to perform some operation. The host got the request, or maybe didn't. We got some network exception, and now we can't access the host that we sent the request to. In that situation, we can't know what happens with the operation. Did the host, as the host received it and start to perform it? Didn't he receive it? Maybe the operation was inserted to the jobs queue in the host. We don't have a way of determining what happened. So as part of the SPDM approach, we also added job fencing. What is job fencing? Job fencing allows us to prevent from a host to perform operations if it still didn't start to perform it. For example, if I send copy request to one of the data center hosts, then that host crashed and I don't know if it got the request or not, I can use fencing to prevent the operation from being executed even in the future. If, for example, the host wakes up after 30 minutes and decides that he wants to perform the job. So that's what job fencing is about. It's about blocking that host from performing the operation. So as I said, we use it when the performing host, or more correctly, the host that we sent a request to, is non-responsive. So how do we do that? Basically what we do, as I said, each entity has a generation. So let's assume that we sent a request to host A to copy data between two volumes. Then that request arrived to the host and entered a queue. That host became non-responsive, so the management system has no connection to it. So what do we do in order to finish the job? We send requests to other hosts in the data center, saying that it needs to increment the entity generation. So if we take the example of the volume, we send request once host A that we send the initial copy request to becomes non-responsive, and we know that the operation didn't start yet. We send request to host B to increment the generation of the entity, the generation of the volume. So let's take a concrete example. We send requests to other hosts to increment the entity generation by 5. So if the initial generation is 0, we tell it increment the generation to 5. Okay. And if it succeeds to increment the generation of the entity, we know for sure that the operation will never be performed. How do you know that? Even if host A will start to perform the operation in few minutes, the first thing it will do when attempting to perform the operation is to compare the generation that it was asked to perform the operation on, in this case, generation 0, with the current generation of the entity. It will see that the engine sent the request to perform the operation on volume with generation 0, and now the generation of the volume is 5. So it will silently fail and won't perform anything on the volume. So as we get ACK that we managed to increment entity generation, we know for sure that the operation will never be performed. I just add a quick note here. Obviously, we need to prevent from race conditions from happening. So all those updates and on the entity and the check of the current generation of the entity are performed under a lock. We use Fanlock to perform the locking, but I won't get to it in this session. Okay, so what's the count flows? Sorry for that. What's the count flows using the SPDM approach? Basically, what we do now is that we migrate after we completed the infrastructure required both in the engine and in the VDSM side to implement the new SPDM approach. What we do is that we start to convert flows to use that approach. So all the infrastructure was ready. It required to implement a new infrastructure that allows us to execute flows in the engine, and it required a lot of infrastructure work on the VDSM side as well. After all of that completed, we start to migrate flows to the new SPDM architecture. So move disk, cold move disk, which means to move a disk when the VM is not running, is already using that approach. Add VM from template using that approach as well, or architecture, and cold merge of snapshots using it as well currently. Okay, let's move on to a quick demo to see how it looks in the logs. So just a second. Okay. Okay. So, just a second. Okay. So, okay. So, here's an example. Okay. So, let's start with successful copy. So, we can see here that the user initiated a move disk operation. So we can see that the first thing we do is that the first thing that we do is that we clone the image group volume structure to the destination domain. So we can see that in that case, we first create initial volume. That's the volume creation. Here, create volume container. Then we monitor that operation. When it ends, you can see here that the operation ended. Here is the result of the task. Task 3.5f finished successfully. Then we move on to create the second volume of the image. Here it is. Create snapshot. Here's the second volume creation. We wait for it to end as well. After it ends, we can see that the task to create the second volume ended. After it ends, we have the image ready on the destination domain, and then we start to copy the data to it. So we can see here that cloning of the image structure or the disk structure was completed. You can see the flag. And then we start to copy the data to each of the volumes. So the copy data, as I said before, is data operation, so it can be performed by any host in the data center. So we can see that we initiate the first copy. Here we poll the operation, and we see that it ended successfully. We move on to perform the copy of the second volume. Obviously, we can perform those operations concurrently as well, as they not depend. We can see that the second copy finished as well, and we end the operation. Or more correctly, we delete the source image, which is performed by the SPDM, and eventually we let the user know that the disk move finished successfully. So that's a successful flow. Let's see flow with an error. So, okay. So the same as before, the user initiates a move disk operation. We start with cloning the disk volume structure to the destination domain. We create the first volume. We monitor the task. When the task ended, here, the task ended, we move on to create the second snapshot of the volume. And when the second volume creation ends, we start to copy the data. So in that example, I simulated a scenario in which we don't know if the data operation, the copy operation is running on the host or not. So we can see here that, just a second, we can see here that when performing the copy operation, we can determine the status of the job by polling the entity. That means that the generation of the entity wasn't implemented, so we can't know for sure that the operation was completed. But we can either know that the host won't wake up in the future in case we lost the network connectivity to it, or alternatively, that it will start to perform the operation in few minutes. So we can see that we can't assume, couldn't determine the status by polling the entity. So what we do is that we try to fence the job. So we can see here that the command prints that it attempts to fence that job. How does it do that? It do that by updating the volume. So we can see that we try to update the volume with generation 0. So now we increment it by the predefined interval to generation 3. If we are successful with incrementing the generation to 3, which is performed under lock, we know for sure that the operation will never be performed in the future. So we can see here that while we didn't manage to fence the job, we assume that it's still running. We can't assume that it failed. So we can see here that the fence operation completed successfully. And now we know for sure that the copy operation will never, that even if the host will attempt to perform the copy, it will never be able to. And returning a step backwards to the copy operation, so we can see, okay. So we can see that when we initiate the copy operation, you can see that we specify the generation. So after we implemented the generation, even if the job starts in the future, it will fail immediately because the generation is not matching anymore. Okay. So we can see that after we are done with the fence operation, we let the user know that the flow failed. Okay. So we can see it. So we can see, so on that phase, we can let the user know that the operation failed. Here it is. Failed to move disk test2 to domain SD6610. Okay. So I'm going back to the presentation. Just a second. Okay. So, okay, we saw the quick demo. So what are our future plans? So right now, what we do is that we convert more flows to use the new infrastructure and architecture. In some of the cases, it means to write the flows from scratch in order to separate the operations to data and metadata operations, as we talked about before. Another thing that we plan is to improve the job distribution between the data center hosts, between the data center hosts. The next phase. So basically, the current architecture of the SPDM solved or improved many of the issues that we had. Basically, we improved our scalability because now we can copy a lot more of this or perform operations that involves a lot of I/O concurrently, as we perform the operation by all the hosts in the data center. Actually, we performed some scale tests that showed great improvement. The next phase of the SPDM approach, I'm going to step backwards. So we improved our scalability. Because we reduced the load from the SPM, we reduced the chances of encountering failure on the SPM dramatically. So because before all the operations were performed by the SPM, the host was under constant load when there were a lot of operations in the data center. Now the load on the host is much lower. So looking forward, we may eliminate the SPM role completely, and by that we'll avoid single point of failure. But that's future plan. That's phase 2 of the SPDM. That's it. So we have some time for questions. Thank you, everyone.